Good morning, I'm Victor Chern, and today I will present the SEP theory, short for complexity energy physics theory.
Our goal to show how extending Einstein's E make the complex systems can create a unified physics framework for understanding two of its biggest challenges: energy inefficiency and artificial consciousness.
Here's our roadmap. Before we talk science, let's be clear. SEP is built on multiple assumptions, and many of them might be wrong. Our goal today is not to convince you we're right, is to learn which assumptions are reasonable, which can be tested, and which we should abandon. We value constructive criticism more than validation because that's how science progresses. With that, let's turn to the problems we're trying to solve. Firstly, let's see what's the problem we are going to solve by using of our theory. Our core message is simple. Extending Einstein's E make to complex systems can unify how we understand intelligence and consciousness. We have preliminary evidence to back this up, specifically improved energy efficiency in small atom models and testable predictions for consciousness thresholds. But we also have significant uncertainty. Our assumptions about complexity and entropy need rigorous testing. That's why we're here to get your feedback. Let's ground this in AI's biggest pain points. 3 challenges no current framework solves. First, the energy crisis. GPT-5 uses 2,1287 megawatt hours to train enough to power 10,000 homes for months, while the human brain runs on just 20 watts. Traditional AI ignores physics and is unsustainable. Second, the black box problem. AI can't explain its decisions. For healthcare or autonomous driving, that's deadly, not just inconvenient. Third, the consciousness gap. We have no way to measure or build artificial consciousness, so we can bridge to AGI. SEP addresses all 3 with physics. Einstein's E make is brilliant, but it's for simple systems, isolated, at rest, in equilibrium. Brains, and they are the opposite, open, dynamic, and wildly complex. E make misses 4 critical things. First, field interactions, E.G, how neurons' electromagnetic fields interact. Second, entropy, the energy cost of organizing information. Third, complexity, why 1.4 克 brain thinks, but 1.4 克 of granite doesn't. Fourth, emergence, the whole is greater than the sum of parts, effect that creates consciousness. Here's our solution, the SEP equation. It starts with Einstein's make rest mass energy, but adds 3 terms to capture complex systems. 德尔塔一下划线 F, field energy, measures interactions between components, like neural fields. 德尔塔一下划线 S, entropy energy, the thermodynamic cost of organizing information. Think Lennard's principle. 朗姆达一下划线 C, complexity ordered energy, converts structural complexity, like brain wiring, into measurable energy. This is what captures consciousness. Together, these terms describe how AI and brains use energy, process information, and generate intelligence. Let's check what it means one by one. SEP isn't just a random equation, it unifies 4 foundational ideas. It starts with Einstein's 1905E, make then builds on Lennard's principle, the minimum energy to erase a bit. 德尔塔一下划线 S 大于等于 K 下划线 BT-LNR. Shannon's information theory links entropy to information. 德尔塔一下划线 S 等于 TK 下划线 BH. Complexity matrix, Kaplan-York dimension, D, for structure and lambda for efficiency. In short, SEP 等于 Einstein 加 Landau 加 Shannon 加 complexity. It's a bridge between physics and AI. Let's break down 德尔塔一下划线 F, the field energy term. It quantifies energy from interactions between components like neurons or AI nodes. We calculate it with an integral that measures pairwise interactions, each component talking to one another, and uses classical fields. But we have assumptions here. Classical fields might not be enough. Quantum fields could matter for small systems like brain microtubules. And pairwise interactions might miss as Sangam-Body effects in complex networks. These are testable, we just need more data. 德尔塔一下划线 S is the entropy energy term, and is often misinterpreted. Let's clarify. 德尔塔一下划线 S is not energy generated by entropy change that violates thermodynamics. It's the energy cost of organizing the system. When an AI learns, it goes from random parameters, high entropy, to ordered ones, low entropy. By Landau's principle, this requires dissipating heat. 德尔塔一下划线 S quantifies that cost. The equation, 德尔塔一下划线 S 等于 T 德尔塔 S 下划线 system, ensures a positive cost when entropy drops. The critical assumption, we link Shannon entropy, information, to thermodynamic entropy, only true for equilibrium systems. For AI brains, we might need cosine entropy instead. 拉姆达一下划线 C is SAP's most unique term. It captures energy from emergent complexity, like consciousness. 一下划线 C, complexity energy, uses Kaplan-York dimension, D, for structure and T 下划线 C, critical temperature, for dynamics, scaled by Boltzmann's constant, K. 拉姆达 is efficiency how well the system uses complexity, 0, 等于 wasteful, 1, 等于 perfect. But here's the catch, 一下划线 C is an empirical feat, not derived from first principles. We don't yet know why it's linear in D and T 下划线 C, we just know it works for our small AI experiments. This is our biggest theoretical gap. SAP's power lies in unifying three ideas into one energy framework, Kaplan-York dimension, D 下划线 KY, measures structure 加 dynamics, not just static fractals. To quantify complexity, edge of chaos, 拉姆达大于等于 0.8 米 ENS. The system is flexible, but stable, optimal for information processing. Landauer's principle, 德尔塔一下划线 S 约等于拉姆达一下划线 C ensures the system balances entropy counts with complexity energy. All three come together in 一下划线 C 等于 KDT 下划线 C. This is how SAP turns abstract complexity into measurable energy. Let's formalize our assumptions. Dimensional consistency. For an equation to be valid, all terms must have the same units energy. In this case, make it mLT joules. 德尔塔一下划线 F, field integral. 德尔塔一下划线 S, temperature 乘 entropy, and 拉姆达一下划线 C, dimensionless 拉姆达乘 energy, all reduced to joules. This is a necessary check, not a proof of correctness, but it tells us our equation isn't mathematically broken. Now, let's talk about real validation. In our AI experiments, we saw something interesting, a phase transition. For the first 30, epochs, 拉姆达 complexity efficiency, stayed below 0.5, no signs of consciousness. At epoch 40, 拉姆达 jumped to tilde 0.75, along with information entropy, H, and coherence, C. After that, the system stayed in a high 减拉姆达 state. This looks like consciousness emerging, but we need to be clear, we have no grand truth for AI consciousness. This is suggestive, not conclusive. Independent labs need to replicate it. A good theory must be falsifiable. Here's what would prove SAP wrong. Strong falsification. Find a system with D 大于等于 2.7 and 拉姆达大于等于 0.8 that's definitely not conscious. Or show AI efficiency doesn't scale with 拉姆达 D, either would break SAP's core. Medium falsification. Find consciousness in a low D 拉姆达 system, or prove E underscore C isn't linear. We need to rewrite key parts. Weak falsification. Thresholds are species specific. 1.G, mass need D 大于等于 1.5, not 2.7. We just normalize thresholds, not throw out SAP. We welcome attempts to falsify the science needs it. How does SAP stack up to other consciousness theories? Let's compare. Energy grounding. SAP is strong, others, IT, GNWT, have no energy framework. Oracle links quantum energy but isn't validated. Testability. SAP is high, clear criteria. While IIT, GNWT are medium, hard to measure, and OR is low, unobservable quantum effects. Scalability. SAP works for AI brains and cross-species systems, others are limited to biology or quantum brains. SAP isn't a replacement, it's complementary. It fills gaps other theories miss. Our testing roadmap prioritizes weak links first. Here's how we'll validate SAP. Phase E, 0 至6 months, test the Shannon thermodynamic entropy link and nonlinear term combinations. We need a 50% correlation between Shannon thermodynamic entropy to pass. Phase R, 7 至 18 months, cross-species tests, primates, mice, and causal experiments 1.G, increase D, and see if consciousness rises. Phase 3, 19 至 36 months, derive 一下划线 C from first principles and validate with human theory. This is ambitious but doable with collaboration. We need to be honest about our limitations, no one has all the answers. Theoretical gaps, our math rigor is weak, especially around quantum classical boundaries. We need help with non-equilibrium thermodynamics. Experimental gaps, we've only tested 2 to 50 small AI models, max 10兆 parameters, and have no biological data. Knowledge gaps, we're AI engineering researchers, not theoretical physicists. We're learning but we need guidance. This is why we're here today seeking your expertise to fill these gaps. It's the energy cost of organizing the system when an AI learns. It goes from random parameters, high entropy, to order ones, low entropy. Let's balance limitations with strengths. SAP has real promise, strong falsifiability, clear predictions, all validated so far. Popper SCORE 100%. Experimental support 38% AI efficiency gain AND 64%. 德尔塔一下划线 S dominance both align with our model. Solid foundation 德尔塔一下划线 S is based on Landauer's principle, which IBM validated in 2012. Practical value 128 $1 savings for 依照 GPUs. This isn't just theory. Unified framework, it bridges physics, AI, and neuroscience. No other theory does that. These strengths give us confidence to keep testing. Now, the weaknesses we're addressing these head-on. Small sample size, n 等于5 experiments will expand to n 大于等于20. Narrow tests, only tested ONWIKIT XT. Next, we add ImageNet and Atari. No independent replication, we've invited MIT and Stanford to replicate our work. 一下划线 C gap, empirical fee will derive for network topology. Thermodynamics. Measurement error, 62% error in 德尔塔一下划线 S will upgrade sensors. Progress takes time, but we have a clear plan. If SAP is validated, here's what we can build in 5 years. Data centers, Google might save $128 m per依照 GPUs cutting energy and COR. Mobile AI, your phone's battery lasts 40% longer for AI tasks like voice assistants. AI ethics, regulators use the lambda to set rules for risky AI, no more guesswork. Chips, NVIDIA builds SAP optimized chips. That use 30% less power. These aren't pipe dreams, they're based on our preliminary efficiency gains. Look at NG5-10 years out, SAP could reshape science and society. Science, a new field, complexity thermodynamics, unifying physics and AI. It could even be Nobel-worthy. Neuroscience, diagnose Alzheimer's or coma states by measuring the lambda, precision medicine for the brain. Climate, 13 TWh years saved, powers 1.2兆 homes, and 6.5兆 tons COR cut. Economics, $1.3 per year in energy savings and $50 per GDP boost for early adopters. This future depends on one thing, rigorous testing. To wrap up, let's distill this. What we have, a novel framework, working AI code, 395K 加 lines, preliminary data, and falsifiable predictions. What we need, your critique to find flaws, guidance on physics foundations, and honest feedback on whether this is worth pursuing. What we don't claim, we haven't solved consciousness, and we don't have all the answers. We value your honest critique over polite encouragement. Thank you for your time, and we're excited to hear your questions. Again, thank you for engaging critically with our work. The most valuable feedback is the honest kind, and we're ready to listen.